A pendulum having a bob of mass m is hanging in a ship sailing along the equator from east to west. Find the ship when the ship is stationary with respect to water, the tension in the spring is T naught. Find the speed of the ship due to rotation of the earth about its axis. Fine. Now first of all, let's say this is my earth. Okay. Try to be a bit imaginary while drawing the sketch so that you can understand that what actually is happening. Fine. This is my north, this is my south, let's say this is my west and east. Okay. Now I'll see from here. Okay. And now I'll make the diagram. So it will be something like this. That this is my east and this is my west, and it is traveling like this over the surface. Fine. The ship is over here somewhere with a pendulum. Fine. Now initially it is I'll consider that it is rotating with the speed omega naught. That is the earth, that is the rotation due to the earth axis. I have to calculate the speed of the ship due to rotation. Fine. So of course that will be given by, let's say this distance is r, so we will be simply given by r omega, because initially we considered that rotation is only due to the axis of the earth. So the linear velocity will be given by r omega. Fine. In second case, we have to calculate the difference between T naught and the earth attraction on the bob. Now the earth's attraction is mg. Fine. Now since it is moving from east to west at condition of equilibrium, that is along this axis, I can write T naught is in our direction, mg is downward toward the center, and of course a centripetal force that will be given by m omega square r. So I can write mg is equals to T naught plus m omega square r, and I have to calculate the difference between T naught and the earth attraction, that is mg minus T naught. Earth attraction and tension, that is given by m omega square r, where omega is the rotation of the earth and r is the radius of the earth. So that is the answer again. In C part, if the ship sails at a speed v, what is the tension in the spring? Okay, now if the ship is sailing at a speed v, and the earth is also rotating with an omega, fine. So let's say the surface of earth or the surface of the ocean, the linear velocity of the surface of the ocean will be r omega, fine, and the speed of the ship is v. So the relative velocity of the ship with respect to the earth will be given by v minus r omega. Fine. So I'll calculate the actual omega with which the ship is rotating now, and that will be given by v minus r omega by r. Fine. Now again applying the condition of equilibrium, that is mg is equals to T naught plus m omega square r. This was the initial condition, fine, when it was rotating with an omega. Or else, I mean, rather not to go this way, fine, I can write that T will be equal to T naught minus omega square r, fine, omega se, fine. I can write this way, because now what is happening is that the speed of the ship is increased. Earlier it was rotating with the speed of the rotation of earth, now its speed is increased, so its centripetal force was increased, so its tensile will decrease, and the tensile will be decreased by this very amount. So T naught minus omega se, that is v minus r omega by r whole square into r, fine, r square. Okay, so what I can write is T naught minus v square plus r square omega square minus 2v r omega by r into 1m is missing over here, r square r into m. Fine. So just solve this. We'll ignore v square and r square omega square, because we know that omega is of the power of 10 to the power minus 5 and its square. Okay, so it will go to 10 to the power minus 10, and of course we can ignore it. And again the velocity will be also in the same ratio to that of omega, so it can be also neglected. So the tension will come out to be 2v r and this r and this r is cancelled, this r and this r will get cancelled, so 2v omega m, that is the approximately answer, right?